All right, so a quick exam review, which won't be quick. Who are we kidding? But let's go over the exam this way. That way you can go through it. You'll know what you got wrong. And then you can use what you got wrong to prepare for the final. All right. So the first question asked you which of these answers was incorrect. And all of these answers are just the definition of the term. So the answer, the correct answer is actually all of these statements are right. Because energy is the ability of a system to do work. Or all the individual little motions of the molecule is what we consider work. So the energy is a measure of that. The heat is a measure of the total energy. So if you sum up all those little energies, you'll end up with the heat. We measure the heat with the temperature. So the temperature is a measure of the average kinetic energy of all the particles within an object. So we start with energy. Heat comes from energy. Temperature comes from heat. And then enthalpy also comes from heat. So enthalpy is a measure of the amount of heat evolved per an actual amount of substance, generally 1 mole. All right, so the second question asked you what happens if we have a closed system in terms of things that can be transferred. So since this may show up on the ACS final, we'll go through all the different types of systems and then we'll talk about why the answer was right. So here I have a hot plate, and on my hot plate is sitting a beaker, and we'll just assume that there's water in my beaker. So my beaker's open, there's no lid on it. So as it's heating, eventually some of these liquid water molecules are going to become gas molecules, and they are going to go out into the surroundings. Okay? So all those little steams molecules are actually waters. So they're little tiny water molecules. And so when the steam escapes, we have matter escaping. If I were to touch this beaker would be super hot because it's full of boiling water. So I have energy that's being transferred in and out of the system. Again, this is an open system because I don't have a lid on it. All right, so let's say I put a lid on it. Lid. Okay. And so now the water's still boiling, but now when the water molecules get up to the lid, they fall back down. So now my matter can't escape anymore. But my energy still can, because there's nothing to keep heat from getting around the outside of the glass. So in a closed system, I have energy or heat that can be transferred between the system and the surroundings, but the matter can't. The matter stays within our system. So the other option that you would have then would be an isolated system where we put some kind of insulation around here. Okay, so think foam insulation that you have that keeps your house nice and cool. Okay. So if you isolate a system and you insulate it in some way, you have to change these arrows for the heat and the energy. Because now what happens is that you still have the energy, right? Let's fill in our insulation so it looks like we know what we're doing. All right. So you still have the energy, but when the energy gets to the insulation, it just bounces back. Okay. So now nothing can escape. Your matter can't escape because when it gets to the lid, it falls back down to the system. And now your energy can't escape because you have it insulated in something. Once it hits the barrier, it has to come back into the system. So in an open system, both matter and energy can be transferred between the system and the surroundings. In a closed system, which is what this question was talking about, only heat or energy can be transferred between the system and the surroundings. And in an isolated system, nothing is transferred. So neither heat nor energy are transferred between the system and the surroundings. All right, so number 3 on the exam wanted you to calculate the heat of formation of this reaction. And then it gave you some delta H of formation values for the individual compounds. It gave you in a list, a vertical list, and I've written them horizontally under the unbalanced equation, but it still gave them to you. You'll note that you don't have one for oxygen because we wanted you to remember that it's actually 0 because O2 is an element and elements are technically not formed, so you don't have a heat of formation for them. So they're going to be 0. All right. The question did tell you that it was unbalanced, so that means that you're probably going to have to balance it first. So I got 2 carbons. I need 2 carbons over here. I have 4 hydrogens. I'll need 4 hydrogens over here. This gives me 2 oxygens, and another 2 oxygens gives me 4 on that side. So I have to double that to give me 4 on the reactant side. And so now I should have a balanced equation. If you didn't balance that, then you got the wrong answer, because to figure out the heat of formation of a reaction like this, we have to take the sum of the products times their stoichiometric coefficients minus the sum of the reactants times their stoichiometric coefficients. If you would have just had a 1, then you're missing stoichiometric coefficients for both of your products. All right. So it's going to be the sum of the products times their coefficients, which I'll just call N, minus the sum of the reactants times their stoichiometric coefficients, which I'll call N as well. All right, so I'm going to take all of my products and put them in a single bracket. I have 2 moles of carbon monoxide. Carbon monoxide has a heat of formation of negative 110.5, and the units are kilojoules per mole, which is good because the problem tells me to give you my answer, or give me my answer, I guess, in kilojoules per mole. My other product is water. There are 2 moles of it, and its heat of formation is 242 kilojoules per mole. Those are all of my products, so I'm going to close my product bracket. I'm going to open my reactant bracket. I only have 1 reactant, and there's 1 mole of it. So I have 2 times negative 110.5. You would add that to 2 times negative 242. Whatever the sum of that is, you would subtract 52.3 from it. And then when you do your math, you get an answer of negative 757.3, I believe it is, kilojoules per mole. The closest answer on the exam was 757, so it was pretty close. All right, so this next one was about as straightforward as we can make a calorimetry problem. It wants to know how much heat is evolved when you raise a 25-gram piece of copper, and it gives you the specific heat for the copper from one temperature to another. So since we're looking for heat, we're going to be looking for Q. Remember that mass is generally in grams, especially when your C is in joules per grams degrees C. And then your delta T here is going to have to be in degrees Celsius. We're given a mass in grams, so we don't have to do anything with that. We're giving the specific heat of copper in units that match the units of everything else. And then we need to go from we need to know the difference between 48.5 and 22 degrees C, which is 26.5 degrees C. So all you have to do is 25 times 0.39 times 26.5, and you get a value of 258.375 joules, grams canceled, degrees C canceled. So your answer should be in joules. So this next one wants to know how much heat is produced when you have a certain mass of a sample if you are given the heat of reaction for the reaction itself. Now remember that your heat of reaction, which is negative 890 kilojoules per mole, is in terms of the amount of heat released, or kilojoules, per every 1 mole of reactant. So if you look at this problem, we're burning methane, or CH4. So 890 kilojoules are released for every 1 mole of methane we have. But we don't have 1 mole of methane. What we have is 22.5, hopefully anyway, yep, grams of methane. If I can get this grams value to a usable number, I can actually cancel out the moles here and I'll be left with the amount of kilojoules of heat released per mole of our sample. So the molar mass of methane is going to be 12 plus 4, or 16 grams for every 1 mole. So I have 1.41 moles of CH4. So now all I have to do is take this number, which is the delta H, and multiply it by 1.41 moles. That's going to cancel that out. And my answer is going to be negative, because it was negative to begin with. There's nothing that would have changed the sign. 1,255 kilojoules. So positive 1255 was another answer, and that was to see whether or not you need to carry your negative over. But other than that, the math on this one's pretty straightforward. All right, number 6 wanted you to tell me what happens to the wavelength when the frequency goes one way and vice versa. So remember that on your, when we're talking about a wave, the wavelength is the distance between the top of a wave and the top of the next wave. Right? The frequency is a measure of how many times you can get from the top of the wave to the top of the next wave in a given amount of time. So if I drew a second wave that looked more like this, this would have a shorter wavelength than the one above it. And if I considered this and this, the amount of time I'm looking at, then when we have a longer wavelength, our wave doesn't repeat as much. When we shorten the wavelength, our wave repeats more. So as wavelength decreases, frequency increases. And as wavelength increases, frequency decreases. Wasn't part of this question, but keep in mind also that as wavelength decreases, the energy increases because your wave has to be more energetic to repeat more often. Okay, so just think of it as 2 athletes. This athlete's running faster than this one, right? So this one is expelling more energy than this one is who's going nice and slow. So now we have a problem with light and energy. It talks about an electron that has been excited to a certain wavelength and then wants to know how much energy is emitted as that electron falls back down to the ground state. So you had to remember a couple equations here. The speed of light is equal to the wavelength times the frequency. And then you also had to remember that energy is equal to Planck's constant times the frequency. You have to remember them both because in the problem, you're given the wavelength and we want the energy. But we can't get directly from the wavelength to the energy. We're probably going to have to stop in the middle, which is the frequency. So let's start here. And the problem gave you the wavelength in meters, so you didn't have to recalculate it. The speed of light's 2.998 times 10 to the 8th meters per second. That's going to be equal to the wavelength, which is given in the problem, 2.676 times 10 to the minus 7th meters. And that's going to be equal or multiplied by the frequency. We're going to solve for frequency by dividing both sides by the wavelength, because algebra. When I do that, I get an answer, 1.12 times 10 to the 15th 1 over seconds. Remember that this is the frequency, so we're not quite done. We're halfway done. We now have something that we can plug into this equation and solve for energy. So let's do that. E is going to be equal to Planck's constant, which is 6.626 times 10 to the minus 34th joules times seconds. We're going to multiply that by nu, or the frequency. When I do that, my second should cancel and I should be left with a value in joules. And that value, 7.43 times 10 to the minus 19th joules. All right, this one needs to know, in this one you needed to tell me which of these definitions or equations or ways to figure out the principle in quantum numbers is incorrect. The answer for that is actually the angular momentum quantum number, because if you go through, you can see that at the very end of it, it says that the L should be equal to n plus 1. The L is actually equal to n minus 1. All right, so here we have a bunch of electronic series, right? And it looks super crazy, and this is what a spectroscopist might look at if they needed to know what emission series they were looking at. But what all you needed to do was look and say, okay, which one has any transitions from 2 to 1? Because those transitions are going to be the biggest energy, the biggest gap, highest energy. So to determine which series that is, just look under there. The names of them are written under each of the individual series. So the Lyman series is the only one that contains any transitions between the second energy level and the first one. So it's the only one that's going to have the most energetic transitions. All right, 10 wants to know how many electrons are on the third energy level of a phosphorus atom. So the easiest way to figure this out is to write a quick electron configuration for phosphorus, which would be, it would be neon 3s2 3p3. Now the key word here was the third energy level, because the S and the P both are on that third energy level. So the answer is not 3 valence electrons. The answer is going to be 2 plus 3, which would be 5. So there are 5 valence electrons in the third energy level of a phosphorus atom. Okay, this next one wanted you to tell me what L would be associated with a cloverleaf or a d orbital. And so here's your picture of the d orbital that you were given on the exam. Remember that L equals 0 for an S, L equals 1 for a P, L equals 2 for a D, and L equals 3 for an F. So you only have one option that you could use here, which would be L equals 2, because you have a d orbital. All right, so what if you had gallium, which is Ga, and you had to tell me the quantum numbers for the last electron added to an atom of gallium? Well, first you'd have to figure out where gallium is, and you would see that its very last electron would be the 4p1 electron. So it's the first electron in a p orbital. You can get all of your quantum numbers from this 4p1 configuration. 4 is going to be equal to the n, okay? This is your energy level. P, you can determine L from. Since you're in a p, you should have an L of 1. So that means our first two quantum numbers are going to be 4 and 1. As long as this third one is anywhere between -1 and 1, with 0 being the only thing in between, and this last one is either +1/2 or -1/2, then you have a quantum number for the last electron added to gallium. The option you were given was 4, 1, 0, and +1/2. So this question wants to know which one on this list is going to be easiest to ionize. That means you got to figure out which one would be most likely to form a cation. Remember that as you go down the periodic table, as you get larger and you're adding energy levels, it's easier and easier to remove an electron from the atom. So the biggest one down the periodic table and the one furthest to the left of the periodic table should be your correct answer. Another much easier way to say that would be the one closest to cesium is going to be the correct answer. Rubidium is the molecule on this list that is closest to cesium. All right, so which of these is isoelectronic with a sulfur 2- ion? So a couple ways you could have gone around about this, and this is kind of the longest way. So if we had the electron configuration for sulfur, we would see that it's neon 3s2, 3p4. So we are 2 electrons away from a full p shell. That means we're probably going to add 2 electrons to it. And so the sulfur 2- ion, let me erase that so you don't think that it's sulfur, minus. It's going to be neon 3s2, 3p6, which is the same as argon. Okay. Boy, you really can't see that with this marker, can you? You should throw this marker away. All right. So we are looking for something that would have the same noble gas configuration as S2-, so we're looking for something that would also have argon as its noble gas configuration. So most of you got this right, so the majority of the class got this right. The majority of you who got it wrong picked oxygen. And so if you are in the same column, you automatically can't be isoelectronic. Yes, you have the same charge. O is also a 2- ion. But because it's in the same column, that means it's automatically going to have a different noble gas configuration. So O2- was not the correct answer. The one that is correct is Cl-, because if you look at Cl, it's 3s2, 3p5. So I only need to add 1 electron, and then I end up with argon. Al3+ has a noble gas configuration of neon, as does sodium plus and oxygen 2-. Chromium 3+ has a crazy electron configuration that's not related to any of them. Which one of these would be predicted to be a 2+ cation? So we have a couple rules. One is that the alkali earth metals, or that second column on the periodic table, are going to form 2+ cations because they want to be able to go to the noble gas configuration as easy as possible, and they can lose 2 electrons and get to the noble gas on the row above them fairly easily. We also know that there are some transition metals that can form 2+ cations. Those are a bit trickier. So what I would do if it were me would look through this list and see if there's any of the group 2 or the alkali earth metals first. And there is. So barium was your correct answer here. And you can start ruling out other things if you'd like, but I would just go with the barium and go on with my life. So how many 3d electrons does a copper-1 ion have? Well, let's first start by writing the electron configuration for copper. Its noble gas on the row above it is argon, and this was one of our exceptions. So it was 4s1, 3d10. Now remember, we can also write this in the opposite order, where it's 3d10, 4s1. So we want to know what copper 1 plus is, or how many d electrons copper 1 plus has. And so we need to take one of these electrons from this electron configuration away. Luckily, this 4s shell only has one, so that makes it pretty easy on me. I just take that one 4s electron out, and then I'm going to be left with 3d10. Remember that the superscript here is the number of electrons in your shell. So I would have a principal quantum number of 3. I would have a value of L of 2. And then there are 10 electrons that would have that principal quantum number of 3 and that angular momentum quantum number of 2. 10 electrons in the 3D shell. All right, number 17, or the last multiple choice question, actually was thrown off the exam because I kind of threw that material at you at the end of class, and I didn't. You guys didn't perform terribly well on it. So I just kind of threw it out because I didn't think it was fair. But let's go ahead and talk about what the answer was and why while I have you here. These are the answer choices you were given, not in this order. I've clumped them together by increasing size, and I've clumped them together by charge. Okay. So let's start with the cations, and let's talk about what happens when you take an electron away. So if this is my atom, and this is my electron cloud, I have a nucleus and an electron cloud, right? I have a nucleus of a certain size that's holding on to X number of electrons. Remember, my electrons are negatively charged and my nucleus is positively charged. When I make a cation, I have actually lost those electrons, right? So what happens is that my nucleus, which hasn't changed size, keep that in mind. Your nucleus is always going to have the same number of protons and neutrons, assuming you haven't changed isotopes. So it doesn't change size at all. But you now have more positive charges than you do negative charges, which means that the positive charges you have hold on to the remaining negative charges better than they did before. That forms kind of a contraction. So if this is an atom, then this would be the cation. Cations are always smaller than their corresponding atoms, always. And so you could see how if we went from an atom to a +1 cation, and then we went from a +1 cation to a +2 cation, that we would contract even more. So this guy theoretically should be my smallest one. These guys would be bigger than that guy. Now let's talk about what happens when we add an electron. So if we had an atom here and we added an electron to it, right? Then what happens is now my nucleus, which again has not changed size, okay? All my nuclei are about the same. So my nucleus hasn't changed size. I still have the same number of positive charges, but now it has more negative charges to hang on to. And so my anion is going to be bigger than my atom because it just can't hang on to them as well. Think about this in terms of Jurassic World, where we had the dude with the raptors, right? When he was one-on-one with the raptors, he could actually control the raptors pretty well. But the more raptors he got, the more nervous he looked because it was harder for him to take care of or control what was around him with the raptors. That's kind of the same idea. It's harder for this nucleus to hold on to all the electrons around it if you give it more than what it had before. All right, so that still doesn't answer our question terribly well. So as you go down the periodic table, or as you increase in energy levels, you're going to get bigger. Your atom's going to get bigger. If your atoms were bigger, then your anions are probably also going to get bigger. So chlorine is bigger than fluorine. So now here's the big question, because this is where most of you guys actually got it wrong. Most of you guys just put the one furthest down the periodic table, which isn't the case. Cations are almost always smaller than anions, almost always. The answer was actually chlorine minus, because chlorine minus was the biggest on the list that you were given that formed anions. It will be, the anion for chlorine minus will be bigger than the cation for potassium plus, just because of the contraction of the cations when you lose that electron. All right, let's talk about our heating and cooling curve problem. So first, you had to tell me that this was a gas, that this was a liquid, and that this was a solid. So if you could do that, you got 3 points. The next part of this question wanted you to put the delta H of vaporization where it went with the appropriate sign. So placing the delta H of vaporization in the right spot got you 2 points there. That's where it should go. Now the with the appropriate sign part, a lot of people lost a point here. Because you have to remember that when you're going this way, and we are, because we have a cooling curve here, that we're actually talking about condensation. And condensation is the opposite of vaporization. So you had to give me the negative delta H of vaporization. And what we wanted was for you to put 40.65 kilojoules per mole right here, somewhere around this line, with a negative sign on it. Now, C ended up being worth 3 points and not 2 points, because there were 3 possible answers, and I only made it worth 2 points, which is silly. But it wanted to know which of these segments corresponded to a decrease in kinetic energy. So think about what kinetic energy is. Kinetic energy is the energy of motion. Now, think about what's happening on the curve. If we have a solid and we start to increase the temperature of it, it's eventually going to turn into a liquid. It does that because the molecules are moving faster and faster and faster and faster, such that they can't hold themselves together. They're moving slower here and faster here, then that has to mean a change in kinetic energy. The other part of the question, or another trick that you could have used, was the question said decrease. There's 3 sections on this graph where it decreases, right? And they had letters on them at the time. No, it wasn't C, it was E. So the answer to that was supposed to be A, C, and E, because those are the 3 pieces of the graph that decrease. So which segments describe an equilibrium between 2 states? Well, that's the condensation portion and the freezing portion. So B and D are equilibriums. So you have both gas and liquid present here, and you have both liquid and solid present here. These are equilibriums between 2 states. Now the last one, the last part of this question wanted you to do some math. And it wanted you to calculate how much heat in kilojoules is released when water is condensed from 100 degrees to 1 degree. Okay, is condensed was a key word here, and one many of you missed. Is condensed. That implies that you're going to have to use that, and we're going from 1 degree C, so we're going to have 2 steps, a step here and a step there. Not all of you got the two-step part of the calculation. A bunch of you did, but not all of you did. Now, how do we do the math for the first step? Well, here we're given a delta H of vaporization, and we know, or should know, that Q is equal to delta H times the moles, because I'm given my delta H in terms of kilojoules per mole. If I can get a mole value and get rid of the moles in my delta H, I should be left with kilojoules. Luckily, at the top of the problem, it tells us that we had 250 grams of H2O, and we can pretty easily calculate the molar mass of H2O. So we end up with 13.89 moles of water. So then my calculation here becomes fairly simple. Delta H is going to be negative 40.65 kilojoules per mole, and multiply that by 13.89 moles. My moles will cancel, and I'll be left with a value of in kilojoules, and that value is negative 564.6 kilojoules. All right, so that takes care of step 1. What about step 2? Well, step 2, we're going to have a change in temperature because we're going from 100 degrees to 1. The heat equation that we know that has a change in temperature is our calorimetry equation. Let me back this up a little bit. Q equals M times C times delta T. Came in knowing this. It was also on the first page. But should have come in knowing that. Here my units are joules per grams degrees C. So I was given a value for mass in grams. I can probably still use that. C we know, 4.184 joules per grams degrees C. And I am cooling down, as in a negative temperature, 99 degrees, because I'm going from 100 to 1. With a negative sign here, I'll have an exothermic value for Q, which is what I need. When I get Q, I get a value of negative 103,554, but now I have to be careful because I am in joules and not kilojoules. So here I'm in joules, here I'm in kilojoules. My answer is supposed to be in kilojoules. So I'll go ahead and convert this one by dividing by 1,000. And I'll get a value of 103.554 kilojoules. Now I'm not done. Remember that I was condensing, so I was going from 100 degrees to 1, which means I need to add step 1 and step 2 together. So 1 plus 2. 1. Negative 564.6 kilojoules plus 2. Negative 103.554 kilojoules. And when I add those together, I get negative 668.154 kilojoules. That's a lot of sig figs, so it's probably not the right amount. But somewhere around 667, 668 kilojoules was the correct answer for this problem. All right, here's the super dreaded Hess's Law reaction. And this one was a bit chunky, but most of you got it right, so that was good. So how are you going to go about starting it? Well, what I would do is say, okay, here's my overall reaction. This is what I'm aiming for. This is my puzzle, right? This is what I'm trying to put together. These are my pieces. Boom, pieces. Okay. In my puzzle, this guy is a reactant, and here it's a product. I have 1 mole of them in both places, so I probably don't have to multiply anything. But I am probably going to have to flip this to make this a reactant. So let's do that. C2H4, and I'm going to drop the states of matter just to make my life a little bit easier. Goes to 2 carbons and 2 hydrogens. So I flipped this reaction, which means that I need to flip my delta H. So I need to take my 52.3, that's a point, and multiply it by a -1. Okay? Let me do it that way. That looks less clunky. All right, that's the first step. Now what's next? Go back to your overall reaction. Here, I see that HCl is a reactant, and here, I have HCl as a product. So I'm probably going to have to flip this guy as well. But before you do that, make note of the fact that you have 6 moles here, and you only have 2 moles here. So you're probably going to have to flip it, and then you're probably going to have to multiply it by 3. So let's do it, and let's see if we can do it all at one time without me royally screwing it up. So your product becomes your reactant, and we're going to multiply it by 3. Let me write this down. Flip, multiply by 3. Flip. All right, so then we're going to make 3H2 and 3Cl2, and then let's just quick double check. 6 H's, 6 Cl's, 6 H's, 6 Cl's. So I must have multiplied and flipped. Sorry, yes, multiplied and flipped. So here's my delta H, negative 184.6. I need to take my negative 184.6, multiply it by a -1 because I flipped it, and then multiply it by 3 because I tripled the reaction. Now, what's happening here? Do I need to do anything with this guy? Well, let's go back up here. Here, my CHCl3 is a product, and here my CHCl3 is a product. So that's fine, but I need to note that I have 2 moles of it here, and I only have 1 mole of it here. So I'm going to have to multiply this guy by 2. I do not need to flip it, but I do need to multiply it. So 2 carbons, 1/2 times 2 is going to be 1 hydrogen, 3/2 times 2 is going to be 3 chlorines, and I'm going to make 2 CHCl3s. Now, I didn't flip it, so I don't have to do anything with the sign, but I am going to need to double my delta H. Now, just to make sure that we're on the right track, let's go ahead and add everything together into one big long equation and make sure that we did it right. Reactant, C2H4, reactant plus 6 HCl plus 2 carbons plus a hydrogen molecule plus 3 Cl2s. All right, that looks like all my reactants. Let's start writing down all my products. 2 carbons, 2 hydrogen molecules, 3 hydrogen molecules, 3 chlorines, and 2 CHCl3s. All right, 2 carbons go away with those 2 carbons. Then the 3 chlorines, go away with the 3 chlorines. Here, I have a grand total of 5, and here I have 1. So this guy can go away, and I'll be left with 4 over here. Now let's write things down and see what we get. We get C2H4 plus 6 HCl. That's going to go to 4 H2s and 2 CHCl3s. Does it match? 4 H2s, 2 CHCl3s, 6 HCl's, and 1 ethylene. So it looks like we're pretty good. So I got all these individual numbers when I did all of these individual steps. But then, after I did all these individual steps, I added them together into one big crazy long equation. So I need to do the same thing with those delta H's. So I need to take 52.3 times a -1, because remember we had to flip that. Add that together with negative 184.6. We flipped it. We multiplied it by 3. And then I need to add that together with negative 103.1, and we doubled that guy. So when I do all of that mess, I end up with a value of positive 295.3 kilojoules. It's an impressive amount of math on one screen. Okay. So this question here wanted you to identify the specific d orbitals and then tell me why you identified them the way you did. Now, I told you didn't have to draw any crazy orbitals because they'd be hard to draw, at least the orientation of the different d orbitals, but I did tell you that you had to be able to recognize them. So to the one of you who left me a note, there's your answer to that. Now, we talked, and I said more than once, that when you have the dxy, the lobes of your d orbital, or the leaves of your clover, are between the axes. Similar but contrary to that, we have dx squared minus y squared. And in the dx squared minus y squared, the leaves of your clover lie on the axes. That's literally all I wanted you to do with this one. Be able to tell me dxy, dx squared minus y squared, and tell me that they lie either between or along the axes. All right, so you had to draw me some orbitals. You guys wanted an s orbital, so there you go. S orbital is symmetrical around the axes. This one's not symmetrical at all. That's a terrible drawing. You get the idea. A ball. Okay. You also had to draw me a px. So this got you 2 points. If there was a circle on some axes, you got 2 points. I specifically gave you the pz, and I don't care how you label these because they're three-dimensional axes and they can rotate in space. It doesn't matter which way you do it. But the pz orbital, you got 1 point for the right shape, but you lost a point if you didn't tell us that it was oriented along the z-axis. That's the difference between px, py, pz. They're all the same shape, but they're in different orientations. So you had to prove to us that you knew both of those. 1 point for this, 1 point for that. Last one you had to draw was dz squared, and I'll just leave this here. dz squared essentially looks like a p, but there's a donut in the middle. So if you drew the dz squared orbital, you got that correct. All right, this last one wanted you to look on the first row of the D block, which would be the 3D elements. Find the second element on that row, which would be titanium. The fourth one, which would be chromium. And the sixth one, which would be iron. And then it wanted you to write the noble gas configuration, not the full configuration, for each of these elements. They all have the same noble gas. So they're all going to start with argon. And so now all you have to do is fill in the valence electrons. Titanium has a full 4s, and then it has two electrons, in that 3D shell. Chromium was the exception that we went over a bunch. So you may have put, and a lot of you did, whoops, that should be an S, 4s2, 3d4, but this was the exception we did in class a couple times. So, and we talked about how based on energy, this electron gets promoted to that shell. And so we lose one here and come up with 1, and then we add 1 here and we come up with 5. So 4s2, 3d5 is wrong and got you a whole lot of 0 points. 4s1, 3d5 is the correct configuration here because chromium was one of our exceptions. The iron was included to see if you knew that after chromium, you go back to just filling the S shell like you had before. So iron was 4s2 3d6.